The concentration of solutions can be changed through the process of dilution. When you dilute something, like if you have some juice and it's too sweet for you, you would add more solvent to it without adding more solute. So you would water it down. You'd put more water in there, but the amount of juice would remain the same. So the total amount of drink you have changes, the concentration of the drink changes, but the amount of juice that's in there is going to stay the same. So at the start and at the end, the amount of solute is the same. The amount of solute, if you rearrange this concentration equation, the amount of solute is the concentration times the amount of solution. And so this is what's staying the same, the concentration times the amount of solution. Even though both of these are changing, the concentration is changing, going down, the amount of solution is changing, going up, the product of those two numbers stays the same. So the concentration in molarity, perhaps, times the volume at the start equals the concentration in molarity times the volume at the end. So one way to write this famous dilution equation is M1V1 equals M2V2 for molarity and volume. The concentration can be in anything. It can be in mass percent. It can be in other concentration units that we haven't focused on. So because of that, you'll sometimes see the dilution equation written like this, with C for concentration rather than M for molarity, because it works with any concentration. C1V1 equals C2V2. So you can use either of these equations. I think one thing that's very helpful in these problems is to make a list on the side. Before you put everything in the equation, go ahead and make a list on the side, your C1 and your V1, and remember these go together. This is situation 1. What's the concentration and volume in situation number 1, and what's the concentration and volume in situation number 2? So we have a situation where we have 45 milliliters of a 3.60 molar hydrochloric acid solution. So these two go together. These are the same situation. You don't have 250 mils of the 3.60 molar solution, you have 45 milliliters of it. So it doesn't matter if you make these both 1 or if you make them both 2, as long as you put them both together. So the first situation has a concentration of 3.60 molar and a volume of 45 milliliters. The new situation has a volume of 250 milliliters, and the concentration is what we don't know. That's what we're looking for. So now we can plug everything in. So we have our C1V1 equals C2V2. This is not known, so I kept the variable. Now we can get C2 alone by dividing both sides by 250 milliliters. So that completely cancels. For this part, the milliliters cancel. We're going to be left with molarity as our units. That's good because we're solving for concentration. And we are left with 0.648 molar, 0.648 moles per liter as our new concentration. And this makes sense because we started out at 3.60 moles per liter and we diluted it. So the concentration should go down. Sometimes it's good to make a prediction before you do the problem, saying, am I expecting a smaller or a larger number? And then you can double check once you get that number if it meets your expectation. So let's try that prediction with this problem. So we want to know what volume of 6 molar sodium hydroxide solution if you would need if you were trying to make 350 milliliters of a more dilute 0.850 moles per liter solution. So if we're trying to dilute something to get to 350 milliliters, then what we're starting with should be less than 350 milliliters because we're adding water and we're ending up with 350 milliliters. If we started with more than 350 milliliters and we added water, we're not going to get to 350 milliliters. So this is just what I mean by making a prediction. And then if our answer is not less than 350 milliliters, we can take another look at what we did. All right, let's try making a list here. So the first number I see here is 6 molar. The volume of 6 molar is what's not known. 350 milliliters is not matching the 6 molar. The 6 molar, we don't know what volume of that solution is required. Then the 0.850 molar solution, that's what we know we want 350 milliliters of. So those two numbers match. And if this were your C1 and your V1, that's okay as long as they're together. Because if they're together, they'll be on the same side of the equal sign, and that's what's important mathematically. So if you had switched and put these two on the right and these two on the left, that's okay as long as these two are together on the same side and these two are together on the same side. Then to get the V1 alone, we would divide both sides by the 6 molar. This would completely cancel and leave the V1 alone. This would cancel just the molar, and we'd end up with milliliter, which is good because we want volume. And we end up with a volume of 49.6 milliliters, which is definitely less than 350 milliliters. So this could happen. You take a smaller amount of your concentrated solution, add water, and then you get a larger amount of the dilute solution. Okay, here we have a problem where this volume and this concentration match. This time the concentration is in mass percent. So the 18% sodium chloride solution, we have 36.5 milliliters of that. And then our new concentration is not known. Our new volume is 113.3 milliliters. And then we set that up over here and divide both sides by the 113.3 milliliters. And this side the milliliters cancel, and this side the whole thing cancels. So we're going to be left with percent. That's fine. A mass percent concentration is a way to express concentration. And we're left with 5.80 mass percent solution. I forgot to make a prediction, but we can still check if this makes sense. So we've diluted an 18% solution. We expect the concentration to go down when you dilute something, and it did. We have a lower concentration. All right, let's try to make the prediction for this one. We'll try to remember that. Okay, so we want to know how many milliliters of 3.5% sucrose solution you get by diluting 45 milliliters of 8.5% sucrose solution. So you have 45 milliliters of the more concentrated solution. You're going to add water, and so you're going to expect to get more than 45 milliliters if you add water to that. So that would make sense if you have more than 45 milliliters at the end after you dilute it. All right, the 3.5% matches with the unknown volume, and the 8.5% matches with the 45 milliliter volume. Again, if you had both of these as 1 and both of these as 2, that would work also. Okay, as long as we have the 8.5 and the 45 on the same side, because those match, now we can divide both sides by 3.5%. That gets rid of the percent on this side. We'll be left with milliliters, which is appropriate for finding a volume. And the volume we end up with is 110 milliliters. I haven't really been mentioning significant digits. I've just been using them appropriately. So my calculator is giving me a number with lots of digits. In this particular problem, pretty much everything has 2 significant digits, and this is all multiplying and dividing, so we're going by the number of digits. And so we need to round to the tens place. We bump it up to a 1 because the 9 is very large. So let's try to remember to make a prediction here. So what volume of this more concentrated 12.5% ethanol do you need to make 275 milliliter of the 5% ethanol? So this is the more concentrated one. We're expecting to start with a smaller volume, adding water to get to 275. So here is our expectation. And here is our list of concentrations and volumes. As long as the 5% matches with the 275 and the 12.5% matches with the unknown, then that will work. All right, and here is that problem set up. And we'll divide both sides by 12.5%. And here that gives me a volume of 110 milliliters. Unlike this one where I only have 2 significant digits, this problem has 3. So I can put a decimal here to note that I have 3 significant digits. This one only has 2 significant digits. So even though we're getting pretty far into the course, I want to make sure that people are not forgetting about their significant digits in these calculations.